Really great to have you all at this very end of the day. I'll be talking about or sharing my experience on Spark SQL Catalyst code optimization using function outlining. Before we start off, about myself, I'm Kavana, a senior systems developer at IBM. I have majorly worked on AX operating system development and then looked at Apache Spark and Alexio optimization for power systems, and currently looking at MLDL frameworks for enterprise systems. Co-presenter Madhusudanan has not been able to join me, so he is in STSM at IBM Systems. Coming to the outline, so this is about we are majorly concentrating about the optimization for code generation of the Spark SQL Catalyst optimizer. So this presentation has been outlined so that we recollect the SQL Catalyst optimizer in depth to an extent, and then look at some internal workings of Java JIT compiler, and then go and see how function outlining can be applied to Catalyst code generation and the associated performance statistics with the conclusion. So this is little more on the system side as we concentrate on the performance of aspects of the execution of the applications. As known to all, Spark SQL is the module for structured data processing on Apache Spark. A query is specified either using JDBC, console, or user programs to the Spark SQL, goes through the Catalyst optimizer, which optimizes the query so that it executes faster than the same being specified with RDD primitives. Yeah, basically this slide shows the different phases of the Spark SQL Catalyst optimizer. It basically starts with a relation to be computed. It is specifically specified using an abstract syntax tree given by the Spark SQL parser or the dataset object. This AST is referred to as the unresolved logical plan, which is then fed to the analysis phase, where the unresolved references to attributes are resolved, from which we get a logical plan. On top of this, standard SQL query optimizations like predicate push down, constant folding are applied to get an optimized logical plan. And then this goes into the physical planning phase where multiple physical plans are generated. Basically here the nodes of the logical plan are mapped to the RDD primitives. We will see with an example in the coming slides. Then one of the physical plan is selected for which the code is generated on the fly. The code generation, the code is generated in Java, and that is compiled using the Janino compiler at runtime. So this we can skip this through as we have already discussed on that. So here is a sample example. It's a sample query and specified in an unoptimized way. Here basically we count the number of rows that are selected from the table people where ID is 1. That is what this query does, but that is specified in an unoptimized way. So corresponding to this query, we have the AST, that is the tree that is generated, which basically projects ID and name from the people table and filters it based on ID and counts the number of rows. Let us see one optimization that is possible for this kind of a logical plan. if you can see from the table, ID and name are first projected and then filtered, which is unnecessary because we will have to deal with more number of rows while projecting ID and name. So, instead if we have the filter first, where we filter the rows by ID and then project the ID and name, it is it is performance wise better. So, the filter is pushed down and you can see the interchange there. Coming to the physical planning stage, here each of these nodes from the logical plan are mapped to the RDD operators that match the Spark execution engine. For example, people, if you see here the people, this node has been mapped to table scan people. This is the RDD primitive that it has been mapped to. Coming to the catalyst code generation. Once all this optimized, we have the optimized physical plan, without even code generation it is possible to execute the query, but that would require to go over the tree one node after another for each row. So, each of these nodes are implemented as separate classes with their own routines in which the logic for each of these are embedded. So, you can see that running this query means executing each of these nodes with their routines invoked. So, there are a lot of branches and virtual function calls involved and also unnecessary memory allocations and deallocations for the rows. So, this it was then decided to have code generation done at runtime itself, so that the logic in each of these operators emerge together under one iterator like this. If you see in one iterator, you have the filter, you are even counting the number of rows. So, it is all done in under a single iterator. So, what is the advantage with this code generation is that you are avoiding unnecessary branches, and also in this kind of a code you can see standard compiler and processor optimizations get enabled. Okay. We have now looked at some background about the Catalyst optimizer. Now, let us get recollect basically on the how JVM works. As you all know, Java is both compiled and interpreted. Basically, the source code is compiled into bytecode, and then the bytecodes are interpreted by the Java virtual machine. The benefit is the platform independence. The drawback is it requires, the bytecodes, running bytecodes is not as fast as running pre-compiled machine instructions. Actually, if you see the any application, generally a subset of the code alone is executed very often. So, the performance of such applications will depend on how fastly that subset of code executes. So, what JVM does is it uses at runtime a compiler to compile the bytecodes of such hot routines into machine instructions. Basically, JVM what does when you invoke a Java application, what does it do is it starts interpreting the methods, and as the number of it reaches a specific number of invocations, it tags such routines as hot, and it will compile the bytecode into machine instructions. Using the execution statistics it has collected for that routine. And one more important thing to mention here is JIT compilers come in two flavors, that is the client compiler and the server compiler. It is basically the difference is in the aggressiveness with which the compilers compile the code. Like the client compilers will compile the code little earlier than the server compilers. So, applications with client compiler will have will perform better initially, whereas long running applications benefit using the server compilers, as it can optimize the code better. It can compile the code better as it has more execution statistics. From Java 7 onwards, a clubbed mode has been introduced, that is the tired compilation mode, where JVM will use both the client compiler as well as the server compiler. That is, at the beginning of the application execution, it will use the client compiler, and as the routines become even more hot, the code is again recompiled by the server compiler. That is how the internals tired compilation mode works. From Java 8 onwards, that is the default mode. Okay. With this background on both Spark SQL Catalyst optimizer and the internals workings of the JVM, let us look at how Spark SQL code generation can be further optimized. Like for that purpose, what we did was we took a standard query that is provided by TPCDS. It is a de facto industry standard. We picked up query 72, and while executing this, we got the performance profile of it. And from the performance profile, we noticed that one of the Catalyst generated code, that is at runtime for the SQL execution, it generates the code, right. Once one of the routines in that code was reported to be hot. So, we then went ahead and tried to analyze the logs from the JVM print compilation flag. Basically, this flag will tell when the JVM will compile the hot methods. And from the logs, we found that the hot routine was tried by JVM to be compiled, but it failed due to code cache being full. It is basically the cache where it will store the compiled code. That cache was full. One reason could be that it was the cache was full. So, then we went to the Spark dashboard and we tried to get the jobs, stage and task correspond that took the longest time, and then we also wanted to see what was that code generated. So, we went ahead and modified the Catalyst code optimizer code generation to log the code that it was generating. So, when we looked at the code generated, we saw that the hot routine was more than 300 lines of code. So, this was the reason, we thought this could be the reason for it not fitting the code cache. So, it was pretty huge. So, we wanted to see if function outlining helps here. Now, what is function outlining? It is basically the opposite of function inlining, where the logic in a huge method is split into smaller logic contained in separate routines. The benefit is that JVM loves small methods because it can it finds them handy to inline them as needed. depending on the execution path. The drawback is there will be extra branches that will be added. So, we wanted to see how this using this how we can whether we will perform better. So, to achieve this what we did was we noticed that the query used basically broadcast has join as sort merge join. So, we had to go and modify the code that is generated for these operators. We tried to split the logic into smaller routines. One problem we came up with was some of these locals that were used in the initial routine was referenced in these smaller routines. So, they had to be made as class private, and we did those modifications and tried to analyze the performance using tired compilation enabled JDK. A little more about the code modifications we had to do. If you see the whole stage code generation for the Catalyst code optimizer, it basically has two major paths for each of the operator, that is the produce path and the consume path. In the produce path, the Java code to read the rows from the input RDDs is generated, and in the consume path the Java source code to consume the read rows, that is the rows that were read during the produce phase has to be consumed. So, that code is generated in the consume path. If you can see the operators, the different operators, first the produce path of the different operators are called, and while returning back the consume path is for the different operators are called. So, on here we have a snippet of the source code to show that the produce path of the sort merge join was modified. If you can see, there was a loop inside a loop. So, this loop was extracted and brought into a separate function here. That is how we try to automatically do function outlining at source. So, post these modifications, here is the way the code generation differs. This was the original code, and this is the modified generated Catalyst code. So, if you can see, this routine process next was more than 300 LOC initially, and with the modification you can see it is hardly around 10 lines with a branch to a new routine where the rest of the logic is contained. So, there are multiple other routines also, but only one of them has been shown here. So, when we measured the performance, we saw around on an average around 13% improvement, which was encouraging. So, we found it to be definitely function outlining helped to be it was useful for such hot routines with huge with more than 300 LOCs. This kind of code generation generally happen with automatic code generators. Generally humans won't write such kind of big routines. It is basically it happens with automatic code generators itself. So, definitely we found function outlining of huge routines to be beneficial, specifically when it is hot and it is unable to be, the JVM is not able to compile it. One thing is automatic split of such huge routines at source is may or may not result in performance improvement because of the additional branches. So, it will be useful if JIT compilers evaluate automatic use of function outlining as needed for hot functions, because they would have what is happening, and they have the information about whether that is huge and whether it is hot, and other things are, all the informations are available to it. So, it might be beneficial if JIT compilers evaluate this inclusion of this. And what we observed also was monitoring and tuning JVM code cache and JIT compiler warm up time also is helpful for tuning the Spark application performance. Some of the options that we found useful, I am listing it here. One is the use of tired compilation mode, that is the default now, and from Java 8 onwards. It is also possible to increase the code cache size. The option has been specified, and definitely it will help if we can tune the number of interpreted method invocations. That is, when the client compiler will start compiling the hot routines, and when the server compiler will start compiling the hot routines. So, if you can tune it, it will be beneficial as per your application need. And then other logging options are useful because it will help you to analyze when JVM compiles these methods, like log compilation or print compilations are beneficial, helpful. These are some of the good reads on the Catalyst. Till now, what are the optimizations have been done for Spark SQL. So, they definitely are helpful. So, any questions?
Hi.
Hello.
So my question is, why did you choose to generate Java source code instead of directly generating Java bytecode, which would have been more efficient since you could skip some of the processing step when compiling the code and running it on the JVM?
No, the thing is, with the splitting was done at the source. The splitting of bytecode, it happens inside the JVM, for which we need to modify JVM. Here we first chose to modify this code generation at source itself first, rather than modifying the JVM. So, what we are suggesting is, we wanted to try was whether modification at source will be beneficial.
Any other questions?
So, hopefully I have answered your question. If not, you can.
Do you have a follow-up?
Thanks. Yeah, so I don't think I understood really what the answer there. So what I mean is that there are some libraries to help you in Java or in Scala indeed to generate bytecode directly. And if you were to do that, that would be more efficient. I mean, since you're doing this during runtime, you would be able to skip some of the interpretation steps that the Java compiler has to do when it parses the Java source code. And also, you might be able to avoid compilation errors of the generated Java source code if you generate the bytecode directly. But it's more tricky to generate bytecode, I guess, for the developer who needs to write that code.
See, the thing is that currently whatever happens is the compilation to bytecode happens using the Janino compiler. So, we are not modifying the Janino compiler for the code generation. We are not doing that. We are just trying to see, instead of the Spark SQL optimizer generating 300 lines of code, can it be split into smaller routines so that we can see any benefits with it. That was the main reason we saw from the performance profile that the issues were creeped up. So, that's what we have tried here. The rest other optimizations might be possible, but the one that is being discussed is here at source, whatever is possible.
I understand.
Yeah.
Okay, thank you.
Anyone else?
Hi. This code that you modify was done on the Catalyst compiler, right?
Catalyst source code, that is the Java code that is generated, that we are modifying.
Okay, cool.
Yeah.
So this you did it on your private. Did you create a pull request or something to merge this optimization to?
Sorry, I didn't hear you.
Was this merged onto the Spark code base, or did you?
No, we have it as in a separate Git repository. Basically, if you see our conclusion, we don't want to directly apply to the standard SQL code generation directly, because if we have seen that it is beneficial only when it misses code, that is code compilation during JVM. JVM compilation, if it is skipping that, then only it is an issue. Otherwise, we will be adding unnecessary branches, which can be costly. So, it may not lead to performance improvements in such cases. So, the recommendation is to for the JIT compilers to opt for this based on the situation.
Okay, thanks.
Is there any easy way to catch these points which you can optimize? It seems like you need to literally look into the JVM and does it doing that compilation, or is it an easy way?
Actually, this is, I mean, since I had to make you understand the what these logs mean, I had to give a bit of internal workings. Otherwise, it's just a log, and you just need to see. You can directly see the logs say that this routine got compiled. I have a sample of such logs. Sorry. See, if you see, this is the sample JVM log, and you can see that these are different levels of compilation. Basically, this indicate whether it was the client compiler compiled or server compiler compiled, and if it has skipped or anything, it will show reason there. So, the logs are pretty readable. Yeah, I understand this is a work of a performance analyst. So,
One more.
So this logging seems very interesting. Is it available also for us to get that kind of logging? Is it built into Catalyst now, or did you?
I have, as part of the references, I have given the access, mentioned the Git repository where we can find the code.
Oh, okay, cool, yeah, nice.
So there's actually no second half for this talk. So if you have a question, now is the time. All right.
If we increase that reserved code cache size property, will that mitigate the issue or completely remove it?
It all depends on the memory available on the systems. If it is limited, then it may not be a choice. So, in that way, this kind of experimentations we will have to do and check. That's where this kind of experimentation seems to be helpful. And recently, I mean, before we started off, there is currently a check in the code. There is one more tunable that has been added in Spark. It was not there when we started it. So that tunable is like, if it is more than, I believe the default value is around 8,000 LOCs or something. If that is the case, it will don't do code generation at all. That is what has been added in the code that I noticed recently. So definitely this will be beneficial in such cases rather than skipping the code generation completely.
Yes. Did you try running this on other JVMs as well?
Other JVMs, no, we didn't get a chance to try. We tried with IBM.
Do you expect that there would be any difference in the results?
It depends. I mean, as I said, definitely if JVM is unable to fit in the code cache, we will see definitely an improvement with this. Otherwise, it is an unnecessary branches that we are adding, and it can result in performance degradation.
Anyone else? All right. Well, let's thank Kavanaugh for this great talk.